So the last presentation, last but not least, is by Professor Lignos about cyclic tests on structural components. So
Okay,
Professor Lignos.
Okay, thanks again. This presentation is supposed to be much shorter compared to ones that we saw today, and essentially it involves the new technical specification that you will see many times that is referenced in the new standard that essentially relates to characterization and qualification of structural components for seismic application by means of cyclic tests. So a little bit on the scope of this document. So the new technical specification on seismic testing essentially contains rules for qualification by cyclic testing of structural components. And these components are intended to be used in design of structures for earthquake resistance, according to the new Eurocode 8. Potentially new elements for use in seismic applications. You saw, for instance, in the presentation by Professor Landolfo, that there have been new joint configurations or new configurations in bracings that need qualification, pre-qualification, and also provides general indications for the definition of cyclic tests that are important. And it does not preclude the development of specific European standards. So the other thing I wanted to say is that this information could be also of interest when you are doing assessment of existing structures, because most of the empirical model formulations are based on test data from literature or new data that somehow have to be developed. So the technical specification includes the sections that you see here and essentially describe conditions for pre-qualification, testing provisions, the loading history, depending on the type of element or device. We saw earlier by Professor Bayer that she discussed a bit the issue of loading history. So this comes here. Test reporting requirements to ensure reliability of information, verification of limit states, as well as the information on instrumentation, because sometimes it's not obvious. I'll show you a couple of examples. And finally, some testing provisions that relate to information that should be reported for material specimens and not actual structural elements or joints or etc. So I will briefly discuss each one of these sections, and so that you can get a basic idea. So I will start with section 4, that essentially relates to conditions for pre-qualification, and essentially involve the loading histories primarily for what we call deformation-controlled quasi-static cyclic testing. But oftentimes, especially when we're dealing with columns or elements that carry axial load, this also involves coupling between deformation and load-controlled quasi-static testing. Generally, we are concerned with planar loading conditions. Now, the number of tests to be conducted should be enough such that we can have reliability of the performance of the element of interest. So in that sense, the number of tests should be established by a relevant authority or the actual national annex, so that we can ensure repeatability of the experimental data. Now, the actual test specimens should have representative geometric and material properties of those that we're going to see on site. And test data, as well as complementary numerical studies and design models, should be sufficient to provide the required deformation demands of structural systems according to Part 1.1, as well as the limits that have been established now in Part 1.2 for DC2 and DC3 behavior. Now, this is an example, like for instance, if you're looking into or using pre-qualified joints that, for instance, have been documented in the new Annex E or Annex G for steel and composite joints, then in this case, there is no further testing required if the actual joints are within the pre-qualification limits. And if similar efforts happen in other configurations, of course, with the evolution of the codes, these pre-qualification limits could be revised accordingly. Moreover, when it comes to the testing provisions in Section 5, this features provisions that essentially involve information with regards to the test subassembly to be used. And this is particularly important because it shall replicate closely the demand and boundary conditions that occur in the prototype structure in mind during the seismic action. And here you see some typical examples on configurations that are actually included in the technical specification, particularly if you are concerned with exterior joint subassemblies or interior joint subassemblies, where usually in those, the points where we actually do these cuts correspond to the inflection points, assuming that these are not moving during a seismic action, which is actually not true, especially when these assemblies experience damage. Or in the case of a cantilever wall system or a column, again, some typical configurations are provided, including some guidance on how these configurations should be mounted on the laboratory floor system to essentially minimize the influence of the boundary here noted with letter A, so as the experimental results, let's say, are deemed to be reliable. Now, moving along, in the testing provisions, there should be what we call a qualification record, where in addition to the subassembly, and the test setup information, there should be explicit drawings with all structural details to be included. And here you see an example on a concrete joint that essentially the reinforcement details should be provided, as well as typical drawing on a steel joint, where here you see that some important information related to welds or the fabrication practice, including, for instance, execution classes, should be summarized to ensure quality control and quality assurance as part of the process. Now, a qualification record should also provide some information on the basic or the expected behavior of the subassembly or element of interest. So for instance, here in this one, we are expecting to measure what we call the story shear resistance with respect to the story drift angle. And of interest in a graph like that would be some characteristic points that some of them are actually used in design, but some others are actually used for verification purposes. For instance, one important aspect here would be to document properly what we call the elastic stiffness of the subassembly or the element of interest. If this is a reinforced concrete element, what would be important, for instance, would be to ensure that you report the pre and post crack stiffness of the element. But then once the peak resistance is reached, what is also important is that at the discrete deformation limits of interest to the part 1-2 that we saw for DC2 and DC3, that some basic information regarding anticipated behavior in dissipative zones. This is an example on steel elements that essentially formulate a plastic hinge near the joint should be documented. So here, essentially, we should include a description of the expected behavior of structural elements as well as the separative zones of the actual subassembly. Now, in section 6, essentially, it summarized the recommended loading sequences that are categorized per material and the element type. And you see here that generally these follows the outline of the new part 1.2 in terms of materials and structural systems. Note that there is a reference to anti-seismic devices, but essentially these links to EN 15129 and EN 1337. And the primary focus is, of course, on conventional structural elements, such as the ones that essentially we saw some of the design rules today. So I will briefly illustrate, for instance, typical load history on beam to column joint, where usually the formation quantity, such as the story drift angle defined here, is going to be related with load excursions that in most cases would be symmetric cyclic, such as to quantify demands up until loss of at least 50% of the peak strength of the respective element. In wood structures, the use of monotonic loading is also imperative because like that we can acquire some characteristic values that help the experimentalist to construct the loading protocol. But because of course loading history effects are important, the technical specification does not preclude the use of other load histories that reflect demands, for instance, at large deformations, if we are concerned, for instance, with incipient collapse and quantifying performance for incipient collapse. Now, for each test specimen, a written report should be provided that, of course, includes the loading history and pertinent deformation quantities. For instance, in a case where a joint is tested, here pertinent deformation quantities could be related to beam contribution as well as the column contribution or a joint contribution to the total deformation. And of course, this is something that relates to the instrumentation that I will describe briefly in a minute. Moreover, verification criteria apply according to DC2 and DC3 in the new part 1.2. And for instance, if you have a reinforced concrete shear wall, you saw earlier that there is this new limit introduced for DC2 structures that when you are looking into a flexural resistance of wall, then in DC2, this should be able to reach 1% radian without any loss of the wall flexural resistance. And you see that in this test, for instance, this is actually achieved. Or if you are looking into an example on a full strength beam to column joint from a steel structure, essentially the hysteretic diagram here, we should be able to identify the relevant points such as the maximum resistance or the resistance at the 20% loss with respect to the maximum, where if we quantify what we call a plastic rotation of the joint for a DC2 construction, let's say, in this case, the respective rotation should be at least 2% radian as described now in the chapter. In this case, you see that it's been fulfilled. So in all this, instrumentation is very important. So in that section, essentially, instrumentation should permit the measurement and the calculation of all pertinent quantities. This should include a drawing that identifies the location of each sensor that should be calibrated as per international standards, and the range of each sensor should be clearly identified. And what is important also is to ensure that the measurements of the elastic deformations of the test rig are also done so that these are removed from the reported results so that the results are not influenced by the test rig, which have been seen in several cases. Now, before I close it, in the last section, there are some testing provisions for material specimens. Indicatively, when it comes to concrete, besides typical cylinder testing at 28-day and at the day of testing, there should be also the geometric properties of the concrete mixture aggregates to be reported, as well as testing provisions for structural and reinforcing steel materials. So these should be done according to EN 10002, and typical measured strength, such as yield strength or ultimate strength, should be clearly identified to be used in strength calculations. Finally, indicatively again, when it comes to masonry, tensile and compressive strength should be determined from mortar prisms. The masonry mortar compressive strength should be again determined according to EN 1015-11. And the shear strength of masonry and shear modulus of masonry should be also determined from simple diagonal compressive tests on masonry wallets. So with that, I'd like to thank you very much for your kind attention, and I'll be happy to answer to any questions.
Thank you very much. I have a question about the topic of repeatability, variability of the experimental results. Is there any recommendation about that?
Yeah, this is, so you're talking about this here on slide 3, right?
Yeah.
So yes, so this is a little bit of a, let's say, touchy issue in the sense that there could be cases where, you know, doing more tests financially could be very, let's say, viable. So in that case, increasing the number of tests could actually be very meaningful. But there could be cases where test specimens could be quite expensive. So in that case, the number of specimens should be carefully selected, as well as the type. Now, historically, again, this depends a little bit on the configuration that is being examined. But usually, you know, I would be a little careful on that, meaning, you know, putting numbers because of cost-related issues, as well as other factors that may come into play.
Because in terms of viability, for instance, perhaps a range of viability may be, for instance, recommended, or?
Yes, so variability, I think to get a sense on variability, I think, you know, it could be good to consult with Eurocode 8 Part 3, where for different, let's say, materials and structural elements, there is now extensive information. I think Professor Kapos eventually will present some of these findings, where there, I think a good addition in the part 3 is essentially information regarding variability, and then based on that, somebody could decide on a number of tests to be done.
Yeah, probably from moving from steel, concrete to timber, for instance, you may have some huge variability.
Exactly.
So I think we can now thank the speakers, all the speakers, for their very interesting presentations.